Okay, in this video lesson, we're going to start talking about how much of our solute can dissolve into a certain amount of solvent, okay? And when we want to quantify this, we actually want to put numbers to this idea. You may have heard the terms like something is saturated or unsaturated or even supersaturated. Those are very generic terms that we talk about in terms of how much solute can be dissolved into a solvent. However, as soon as we get into that quantitative world, we start using this phrase solubility, okay? Yes, we do use the vague term like, hey, this is soluble or this is insoluble, okay? And we have kind of like generalized this ability to dissolve versus not dissolve by saying it's either soluble or not. But really, if you look up solubility, it's a number, okay? It's a numerical amount, and every substance has its own solubility. Even if we consider it insoluble, sometimes there's trace amounts that can still be dissolved into a solution, okay? Now, we report these as a concentration, and we've talked about molarity as one type of concentration, and this unit will cover a few more. But we do look at this as a range of how much solute per solvent can dissolve being in that concentration. We're going to click over here on this link, and this just brings up a Wikipedia page, and it's kind of interesting because you start to look at all these different substances and the numbers that they have in front of them. So for example, aluminum nitrate and its solubility at 20 degrees Celsius, you can get 73.9, and this table is grams per 100 milliliters, okay? Aluminum sulfate is 36.4. Actinium hydroxide is 0.0021, okay? So we would probably consider this an insoluble compound. Yes, a little bit can dissolve, but not very much or a very small amount can dissolve in comparison to, let's say, something like, let's find a big one, like ammonium nitrate, which is almost 200 grams per every 100 grams of water. So you guys can almost put in double the mass of ammonium nitrate into 100 grams of water to get it to dissolve, and all of it will dissolve, okay? This table here is just to show you that there is a bunch of numerical data on the different solubilities and to start to bring up the idea that we have different temperatures here. So all of these solutes here are solid solutes, and they're all going to be temperature dependent. So we see that, like aluminum nitrate again, we can dissolve 73.9 grams at room temperature, but if we brought it up to the boiling point of water, we could dissolve 160 grams, so a lot more. So there is a temperature dependence to our solubilities also, okay? Now, if we go back into our slideshow, take a look at that, we want to talk about this term soluble versus insoluble, okay? When we do that, we're talking about gas or solid solutes in these scenarios. We're not really talking about liquids. Liquids are a little different because with liquids, you have a liquid blending with another liquid, and there really isn't a limit to how much that can happen. It's just more of a ratio or percentage, okay? We sometimes see that in like our alcohols, like our drinking alcohols, where you say something is 80 proof or 40 proof, or there's a certain percentage of alcohol per volume there. And those numbers are really, can be any ratio because with liquids blending with liquids, there isn't a limit to the solubility, okay? In fact, we use a different term for that. We call it being immiscible or miscible, okay? So if you are a liquid that's nonpolar, you would be immiscible in water, meaning that you won't mix with water. That's an example like oil and water. If you're a liquid like ethanol, we say you're miscible, which means that you and the ethanol and water can blend together in any ratio they want to blend with, okay? And we can separate these mixtures out, but there's no limit to them. There's no numerical value that says this is the most you can possibly put in, okay? We do have that for gas and solid solutes. Now, we know that we have these solubilities, so we want to be able to also modify this or see what affects these solubilities. So to do that, we're going to talk about either pressure or temperature, okay? So first of all, for pressure, it only affects gas solutes, okay? Bold this, underline this, highlight it, whatever you got to do. It's only about gases, okay? One of the favorite questions I put on test is I give you a gas and say, I give you a solid and I say, how does pressure affect the solubility? Well, it doesn't, okay? So really, it only has to do with gases. And if we take a look, we have our solubility on our y-axis over here, and then we have the pressure on our x-axis here, and you see three different gases that we'd have at room temperature. And you notice how as the pressure goes up, we can put more gas into solution, okay? This is actually called Henry's Law, and we're gonna watch a little video on why that works.
The solubility of a gas in any solvent is proportional to the pressure of the gas over the liquid. Here we see a gas in equilibrium between the liquid and gas phases. When the gas is compressed, the solubility of the gas in the liquid phase increases in proportion to the increased pressure. The relationship between gas pressure and solubility is known as Henry's law.
Okay, so this goes back to a little bit of our previous units on gases and IMF and equilibriums. If you think about that, if we increase the pressure above a solution, we now have more particles creating more collisions. So more of those particles will then transfer into that solution because of the increased vapor pressure above that solution, okay? We find this in like our carbonated beverages, where if we open up a carbonated beverage and we see it start to fizz, that's because we've released the pressure. So the pressure has gone down, and as a result, less carbon dioxide, a gas, can be dissolved into that liquid, the pop, or whatever we call it, okay? So with that drop in pressure, some of those carbon dioxide goes out. So as pressure went down, it would decrease that solubility. The exact opposite is true, where if we increase the pressure, how they actually get the carbon dioxide to dissolve into the soda is by increasing pressure, which then makes it more soluble, okay? Again, only for gases. Now, looking at this through the lens of temperature instead of pressure, temperature affects both gases and solids, but it does so in a different way, okay? So first of all, talking about gas solutes. When gases dissolve into solution, what we see happen as we increase the temperature, we look at our graph here, we see a very much an inverse relationship. So as temperature goes up, the solubility of the gas goes down, okay? So let's talk about why. So why, if you would warm something up, would the gas particles inside that become less soluble or have less of them in that space? Well, let's look at it through the lens of kinetic energy. If we heat up a solution, that gives that solution more kinetic energy. If that gives it more kinetic energy, what happens to the particle speed? Well, particle speed has to go up. So if we have more particles moving faster, and gases are naturally at a higher energy state than the liquid they're in, right? Gases are higher energy, liquids are lower energy. So if we give them even more energy, less of them will be able to stay in that solution. So with an increase in energy, they give them more speed and more can actually escape or leave the solution, all right? So as a result of the increase in energy, the high energy state gases will leave that solution in an inverse relationship, okay? If we look at the same idea, but now we'll talk about temperature affecting solubility for solid solutes, okay, it's exactly the opposite, okay? But for the same reason, okay? As we increase the temperature, we see all of these things going up, and these are some pretty drastic changes, right? So look at this potassium nitrate. You know, at room temperature, we can dissolve about 30 grams of it in every 100 grams of water. You move it up to just 50 degrees Celsius, or just a little bit above double room temperature, and you can triple the amount of solute you can put in there, okay? This is kind of like how rock candy is made. So you dissolve a whole bunch of sugars at high temperature, and as a result, they dissolve really well, and then you let that sugars and flavoring cool down, and it re-solidifies, and that creates rock candy, because at lower temperatures, less of your solute can dissolve, okay? Let's talk about the why again, okay? We know it's a direct relationship, but why, okay? Well, solids are opposite of gases. As you give solids more energy that are dissolved in that solution, you're giving them the ability to move faster. So if they can move faster, they will break free of their solid state easier, okay? So those ions in solution, or those molecules in solution, won't be bound by their crystal lattice or bound by that intermolecular force holding them together. Instead, they're more likely to stay separate and stay into that solution, okay? So really the same reason, but we're looking at the lens that solids are typically a lower energy state, so giving them more energy helps them stay into that liquid phase of being in solution, and gases are the opposite. Because they're high energy state, increasing their temperature forces them to leave that liquid or that kind of solution. Yes, there are some exceptions to this. You do not need to memorize or remember this exception, but there are some exceptions. And typically when these exceptions happen, what goes on here is as you warm something up, that's affecting the lattice energy of that crystal lattice. So you're actually making it easier for that crystal lattice to hold on to those solid particles. So for some crystal lattices, it gives them more strength, which means less of them can be separated, okay? For us, we just need to realize that there are some exceptions. You really don't need to explain why in this case, but I do want to acknowledge the fact that there are some of those exceptions there, okay? So in this video, we talked about what is solubility. We know it's a numerical value we can look up. We talked about the two things that can affect solubility: pressure, and that's only for gas solutes; temperature, which is for gas solutes and for solid solutes, but they have opposite effects to them. What we didn't talk about is liquids, okay? Because liquids really are not affected by pressures or temperatures or anything, because there isn't a limitation of their solubility, because they're more of a blending of two liquids together. All right. Now, we're going to end the video here, and next time we talk, we'll be more about concentrations.